So these two materials, what you see here is aluminum nitride and gallium oxide. Normally, this is ultra wide bandgap material and well recognized for the power electronic application. Uh, so it has evolved as power electronic materials with the multiple reasons that you have a very increasing demand of EV or let's say handheld vacuum devices, drone technologies which require power electronics, right? Solid state power electronics. And so you need these materials which could be very power efficient. However, there is one more applications where aluminum nitride, AlN GaN technology has worked very good. That is FET-based biosensors, right? And one of the reason it worked very well because it has a very excellent 2D EEG. Taking the cue from there, if we can have a gallium oxide based HEMT or FET, field effect transistor based device, which is sensitive to the surface charges uh, or the variation of the potential at the surface, we can have a very sensitive biosensor, a repetitive biosensor, which is very required for the commercialization of these kind of technology. You can see the number of papers published in this material over the years, and that gives you the significance of this material system. It is growing exponentially. And one of the reasons it could be a very good biosensor because it is very chemically stable. Uh, so with these motivation, we will seeing the potential of gallium oxide for biosensing application. So this is more like the pioneering work where we are looking for the potential, how is it possible to use this material for biosensing. So the working principle we have talked about in the inaugurating talk, how it works, FET-based biosensor. Basically, you have a biorecognition element, we call it probe or bioreceptor, and then you have a target molecule. So you have three elements here: biorecognition element, transducer, and electronic system. Biorecognition element is simply a probe. Then you have biomolecule target, which goes and attached to the probe, gives some potential change, I will say charge change, which is reflected into the potential change, and ultimately that is being seen in the current of the field effect transistor. And then you process those changed value, right? Let's say delta I. Okay? And you can amplify that and then further convert this to the digital form and then process it. That's on to you. So there are many motivation to use this system. First motivation is kind of a 3-nitride integration of 3-nitride with the gallium oxide. 1,3-nitride, which is a very good material for the for today's world, and gallium oxide is being seen as the future of high band gap materials. It's kind of a marriage of present and future. And then theoretically, these two combination gives you physics-wise gives you a very high discontinuity at the interface of these material with the polarization in the 3-nitride, and which is what we saw in our simulation is it is resulting in very high 2-dimensional electron gas. So you see, it is the accumulation of electrons at the interface of these two materials, which can work as a channel for this FET devices. So normally for the AlN GaN material system, which is commercially used, we see the 2D EG of around 10 power 13 per centimeter square. But for our simulation work, we have noticed the 2D EG of around 5 into 10 power 13, which is quite higher than that. And so we expect that higher 2D EG will lead to the highly sensitive sensors. And ultimately, it is the 2D EG or change in the 2D EG which is leading to the sensitivity in these biosensors, FET-based biosensors. This is our device structure, and our current device structure is mainly based on the cavity-based structure. So what we have here is, you can see my pointer here. We have a normal HEMT kind of structure, and then over top of this, you have an oxide layer, and then you have a cavity layer. Okay? So you can put the biomolecule. Then over this, you have a gate structure. So this is my device structure here. And what I want to show here to you next that how much 2D EG we can have in these structures. So this is a simple gallium oxide aluminum nitride interface. And what we are seeing is a good quantum wave formation at the interface, thanks to the very high discontinuity at the interface, as well as high polarization electric field in the aluminum nitride. And so we have got the 2D around 5E13, which is quite high in this section. Normally, you have few used hetero interface which gives you 2DG. One is AlGas gas, which gives you 2DG in the range of E12, AlN which gives you 2DG in range of, I will say, low E13, and this is giving you theoretically in the range of mid E13. There are some assumptions here. Since it's a simulation work, we could not incorporate all the physical parameter. We started with an ideal system here. We assume that your interface is ideal. You do not have any defect there. We assume that aluminum nitride does not have any background concentration. We have a perfect ohmic contact, which is kind of very difficult for any wide bandgap material, but for the simulation purpose, we assumed all these things. And then biomolecule, we model the biomolecule as dielectric material. So we have different biomolecule with the different dielectric materials. So that is very simple assumption. And then that is immobilized, or that is spread into this cavity region of your structure. And that's where you have a change of the dielectric constant, and that might give you different channel concentration and channel current. Moving on. So this is the quantum will form at the hetero interface here in these kind of structure. If you draw a line along this cavity, let's say this is your line, and this is your this is exactly here the hetero interface, this one, right? So what we see here is changing the biomolecules. So normally we are using 4 different neutral biomolecules here with different dielectric constant, namely uric acid, streptavidin, protein, and CHOS. And they have different biomolecules, different dielectric constant, starting from 1.5, around 1.5 to 3.3. And what we see here is different. What I see here is the shift in the quantum well here, and that shift in the quantum well gives you the, gives you the relative position of these quantum well from the quasi-Fermi level, and which will ultimately decide the concentration of electrons in these channels. And so, and what it can be correlated with, this shift can be correlated with the interface electric field at the aluminum nitride biomolecule interface. So if you have different dielectric constant, your displacement vector should be continuous. And if you have a different dielectric constant, epsilon E should be continuous. Epsilon 1 E1 into epsilon 2 E2 should be continuous, right? So if you have a higher dielectric constant, it will relate to the smaller electric field in the aluminum nitride region, and that is the electric field graph, and which is ultimately relating to the channel concentration. So what is happening is higher dielectric constant is resulting in the lower channel concentration and ultimately smaller currents. And that's what we see in the currents, drain current of these FET structures. We assume that this is in the linear region. We are not showing the output characteristic here, but this is in the linear region. And what we are seeing is that increasing the dielectric constant, you are lowering the current, IT. Or I can also say that increasing the dielectric constant, you are also increasing the threshold voltage, mainly because of the channel electron concentrations. So that in itself can give you the sensitivity. Second thing, you can increase the sensitivity by changing the cavity length. So we have also seen the variation of cavity lengths here. And for different cavity lengths, we are seeing the different current, different threshold voltage. And that is the shift of threshold voltage with different cavity length here. Ultimately, you have a different cavity length. And I will say that one side you have the oxide, one side you have the biomolecule, effective dielectric constant. You can just average it out, and that is playing a role here. And this is the sensitivity of the on current. And ultimately, what we see, this value is very important, delta ID, which is in the range of 0.1 milliampere, which is a quite good number. And if we get this number, I don't think we need any amplification at the output. We can directly send it to the ADC simply and process it. So this is a very good number, what we see here. So ultimately, I will go to the conclusion. What we saw here is analysis of these kind of biosensors can have the great potential, but one point which I would like to point here, that we have to develop a physical system, we have to grow a system which can result in high 2D. Theoretically, we are seeing it, but then experimentalists have to develop this system. It may not be aluminum nitride, it can be gallium oxide, different phases of gallium oxide, which can result in high 2D. Thank you.